Okay, one of the most important rates of change that we look at with the calculus is all to do with motion. That's why we had a bit of a look at travel graphs yesterday. Basically, once we had calculus, it just opened up a whole world of discovery with velocity, acceleration. They can look at motion of planets, all sorts of things. So let's look at this in a little bit of detail. Displacement, defined that yesterday. You'll find that the most common pronumeral we use in maths for displacement is x. I think in physics they use s, is that right? Or something like that. And it's defined as distance from a point with a direction. Now I suppose we use x because we just think of something usually moving along the number line, and the number line being horizontal, so think of the x-axis, I suppose. Velocity, different symbols we tend to use depending on the problem. V, obviously, but velocity is a rate of change. Rate of change of displacement with respect to time, so dx to t. But when we're doing motion questions, sometimes we use this dot notation for derivatives. So one dot means the first derivative, two dots means the second derivative, and so on. So x with one dot means the first derivative of displacement. And so it's the rate of change of displacement with respect to time. So it's the speed of the particle, but again, with direction. So the positive or negative is telling us which direction we're going. And then we have acceleration, and even more notations. A, obviously, but it would be the rate of change of velocity with respect to time. So we could have dv to t, but that also means it's the second derivative of displacement with respect to time. So using the dot notation, you could have x with two dots, or velocity with one dot, because it's the first derivative of velocity. So all different sorts of notations we might see for acceleration. Acceleration is the funny one, because displacement is distance with direction. So there's a distinct difference between distance and displacement. Similarly with velocity and speed. Right? Velocity is speed with direction. Acceleration is acceleration with direction. We use the word acceleration in both contexts. Now, this idea of deceleration you might have heard. There is no such thing as deceleration. When people talk about deceleration, what they're thinking about is slowing down. And you are accelerating, but you're accelerating in the opposite direction to which you're traveling. And that is when you slow down. So if you accelerate in the same direction in which you're traveling, you will speed up. If you accelerate in the opposite direction to which you're traveling, you will slow down. Here's a little diagram that I found years ago in a newspaper, and I thought it was pretty good. So it's a little flow diagram. You've got displacement, velocity, acceleration, and I can differentiate to get from displacement to velocity and then to acceleration. But if I want to go back up again, we integrate. Here's a, displacement time graph. So now our travel graphs, if you like, if we're talking about displacement instead of distance, we can have negatives on the displacement axis as well. And it's not a straight line like our traditional ones. Now we can deal with curves. Now, instantaneous velocity. Yesterday we talked about average velocity. So we want to know how fast it's going over a period of time. But when you're talking about motion, you're usually more interested in the speed or velocity you're going at a particular point in time. That's more interesting to find out. I mean, if you're in a car, for instance, and you're driving along and a policeman pulls you over because you're doing 80 in a 60 zone, you can't go, but sir, in the last 100 kilometres, I've averaged 40 kilometres an hour, so I should be okay. No good. It's your instantaneous velocity they're interested in. And remember yesterday we saw the average velocity formula was pretty much the same as the slope. So if I want to find a slope of a curve at a particular instant, then it's the slope of the tangent. So again, the idea of velocity being the derivative at a particular point in time. So the slope of the tangent at any particular point will give you the instantaneous velocity, the velocity at that time. Now underneath, I'm going to draw a velocity graph. And really, it's basically just drawing a derivative graph. So let's draw this one. There we go. How do I know what it looks like? Well, I know that a stationary point will be when the velocity is 0, so they will be the, well, t-intercepts on my velocity graph. I know the point of inflection, well, I'm guessing the point of inflection is about 2, will turn out to be the turning point on the velocity graph. I know when the curve is increasing, the curve is positive, and when it's decreasing, the curve is negative, and when it's increasing, again, our derivative will be positive. And so that gives me a good idea. Another way to think about it, I guess this sort of looks a bit like a cubic. Differentiate a cubic, you get a quadratic, and this kind of looks like a parabola. If I wanted to find the instantaneous acceleration, again, it would be the slope of the tangent at that particular point, because acceleration is the derivative of velocity. And if I want to draw the acceleration graph, I can do exactly the same thing. Now, if this is a quadratic, what am I expecting here? It should be some sort of straight line. But again, I can look at key features. Stationary point, well, it'll be 0 on the acceleration graph, things like that. It's decreasing, so I know it's going to be negative on the acceleration graph, and so on, and there we go. So we get a straight line if I was to translate that down. Okay, example 1, we're going to find the distance travelled. So the distance travelled, remember we've got to go up and down. It's not displacement. So we've gone 2 up, then we've gone down to -2, so that's another 4. Then we've gone up to, I think that's meant to be stopping at -1. So that would end up being 7 metres it's travelled. As opposed to its total displacement, well, it's ended up at -1. So -1 was the displacement. The average speed, okay, that would be the distance it's travelled in that time divided by 4, because there's 4 seconds there. Whereas the average velocity is the displacement over that time. All right. If we can get an equation of that graph, though, we don't really need to draw the graph necessarily, because a lot of key features we can use just calculus. And the words are kind of good too, because if you've got a displacement time and they ask me something like, when does the thing stop? Oh, well, that would be when it's stationary. A stationary point, velocity equals 0, or the first derivative equals 0. So it's kind of nice, those words translate. Displacement of x, there's our formula. We're going to find a formula for acceleration at time t. Just a calculus question, differentiated a couple of times. Differentiated once, I get velocity. Differentiated again, I get acceleration. So we have a formula to find each of those particular features there. Oh, there is. When is the particle stationary? Well, it's stationary when velocity equals 0. Just solve that particular quadratic. And we get at 2 times. So initially it's stationary, and then again after 14 seconds, it'll be stationary again. Now, this all comes into play with acceleration, because if initially it's stationary, which direction am I going to move? Am I going to move in the forward direction, or am I going to move in the backwards direction? Why? Because you sub it in. Sub it into what? Good. At t equals 0, acceleration is -42. So if I'm here stationary, and you can think of acceleration, and we'll talk more about forces later, but force is mass times acceleration. So the force is in the same direction as the acceleration. So if I'm stationary, and then they say, but this force is going to be applied to you in the negative direction, it's like someone's pushing me, well, I've got to go backwards. A particle is moving on the x-axis, kind of handy, starts at t equals 0 from the point x equals 7. That's good, it started at t equals 0. That's 2. When else would it start? Yeah. If its acceleration at time t is 2 plus 6t, find the position of the particle when t equals 3. So we've been told acceleration is 2 plus 6t. I can integrate to get a velocity formula. Now I've done it as a indefinite integral this time rather than a definite one. Velocity equals 2t plus 3t squared plus a constant. When t equals 0, v equals 0. So subbing in, oh, look at that, constant equals 0. Had I forgot my plus c, then I would have got away with it because it turned out that constant was 0. But be careful with that. Make sure you remember your plus c. So velocity is 2t plus 3t squared. And then displacement, integrate again. T squared plus t cubed plus a constant. And this time we know that when t is 0, x is 7. Subbing in, this time I wouldn't have got away with it if I'd forgotten the constant, because the constant is 7. And there's our displacement formula. Now, they want to know when t equals 3. Oh, we now just sub in t equals 3 into our displacement formula that we found. And it's 43. There we go. I like to answer the question. I mean, it was a word problem, so I like to answer it. Reality is you probably, if you finish up with t equals 43, they're going to get that right anyway, but it looks nicer. Answer the question. Now, if I had done it as a definite integral, same problem, I would have said, well, acceleration, that's the same as dv to t. So I know the integral of dv will equal the integral of 2 plus 6t dt. Match up the limits. They told me that when t is 0, velocity is 0. I'm trying to find a formula that links velocity and time, so I'll leave that as v and t. So if I do it as a definite integral, there you go, we get our same formula. Now, velocity is dx to t. So now I know the integral of dx is equal to the integral of 2t plus 3t squared. Again, using the information they gave me, when t equals 0, x is 7. We want to know what x is when t is 3. Okay. You notice this time I did do the square brackets because I've got 7 to substitute in, not 0. So I get x minus 7 is 3 squared plus 3 cubed minus 0. Again, obviously, I come up with the same answer as 43. So I personally think it's quicker to do it as a definite integral, but it's just a matter of choice. If you prefer to do it with it, okay, we'll go find the constants and do all that, by all means. All right, let's have a look at an HSC one. 2001, this is must be a two-nut question, I think. Particle moves in a straight line. Displacement is given by this, wow, lovely formula, t minus 2 on t plus 2. T is measured in seconds. Therefore, what do I know about this particle? Now, it didn't exist 2 seconds ago. Because look, t can't equal negative 2. See? Ah. What is the displacement when t equals 0? Sub in t equals 0, sure enough we get x equals negative 1. So just straight substitution question. So I've actually written that as 1 metre to the left of the origin. You could say 1 metre in the negative direction, or you could just simply say x equals negative 1. All those sorts of answers would be equivalent. Show that x equals 1 minus 4 on t plus 2. Again, remember, 2. All they're really saying is, hey, you can rewrite t minus 2 on t plus 2, and you'll end up with 1 minus 4 on t plus 2. But they do want us to do a bit more. Hence, find expressions for the velocity and acceleration. So, all right, I'm going to show they are the same. Look, 1 minus 4 on t plus 2. That would be t plus 2 minus 4 on t plus 2. Yes, that is t minus 2 on t plus 2. Whilst I'm making light of that, if you do get a question like that, make damn sure you don't stuff it up, because everyone is going to pick up those marks. Okay, well, any average person, I mean, I suppose there'll be some that might get it right. Make sure you get those questions, okay? So, all right, yes, x can be written as 1 minus 4 on t plus 2. So, velocity, we differentiate. Well, 1 obviously goes away. Differentiate a constant, you get 0. I've used the reciprocal here. Reciprocal rule, minus the derivative on the function squared. But, of course, we're multiplied by negative 4 as well. So, I end up with 4 on t plus 2 squared. Then get to acceleration. I can use the reciprocal rule again. Minus the derivative on the function squared. But this time when I differentiate t plus 2 squared, I've got to use the chain rule. So bring down the power, lower the power. diff the inside, minus 8 on t plus 2 all cubed. You may prefer, of course, to put it in index form and do it that way. I mean, it works just as well. Is the particle ever at rest? These are the questions I know you love, because you have to actually use words rather than numbers. You have to give reasons for you to explain. Is this particle ever at rest? There's our velocity formula. Is it ever at rest? Why not? Exactly. We got a fraction on the with a constant on the top. There's no way that fraction's ever going to equal 0. And that's the sort of thing they're looking for. I say, well, hey, that can't equal 0. So no, it's never at rest. What is the limiting velocity of the particle as t increases indefinitely? In other words, what is the limits of this as t approaches infinity, is basically they're saying. Here we go. So limit as t approaches infinity of our velocity. So limit as t approaches infinity of 4 on t plus 2 all squared. What, 0? I mean, if you don't see it straight away, I suppose you could expand the t plus 2 all squared out, and on the bottom you'd have t squared plus 4t plus 4. But remember, when we're doing limits for infinity, all we're left with are the coefficients of the highest power. T squared would be the highest power, so we've got 0 on 1, 0. Another way, if you just think of the graph, if I was to draw that graph, and I know you love drawing your graphs, I'd end up with something like that. There's 4 on t plus 2 all squared. Now I can just look at the graph. Oh, look, that's approaching 0. As t's going to infinity, that graph is going to 0. So whichever way, we get our limiting velocity is 0. So it never is stationary, but it's getting slower and slower and slower and slower. Okay, another HSC question. Particle moves in a straight line. Oh, good. At time t seconds, its distance x meters from a fixed point O is given by, a trig function. X equals sine 2t plus 3. Sketch the graph. Well, in other words, let's sketch this trig graph. So I'm going to sketch a trig graph. Its amplitude is 1. I'm going to shift the thing up 3. The period is pi. So I'll mark off divisions every pi on 4. So there's my axes. Okay. Because I've shifted it up 3 and the amplitude's 1, I know the curve's only going to go between 2 and 4, so I didn't bother with negatives on my vertical axis there. I'll just dot in a line for 3, because that's where the curve's going to wind around for this one. Now, a sine curve, we would normally start at the origin, but we've shifted it up 3, so we'll start at 3, and then a sine curve would go up to its amplitude and down, and so on. There's our curve, sine 2t plus 3. All right. Using our graph, or otherwise, find the times when the particle is at rest. Well, I'm going to use the graph. I mean, we just drew it. I've just drawn a displacement graph. When is it at rest? At its stationary points. And we can pick those up very clearly on the graph. So we know when velocity is equal to 0. So it was at pi on 4 seconds and the displacement was 4. Then 3 pi on 4, it was 2. 5 pi on 4, it was back to 4. 7 pi on 4, it was back to 2. Lot quicker than solving derivative equals 0. Describe, again, you love these. Describe the motion completely. So what do you say? Well, I kind of enjoy myself. I said, and I used a big word there, and spelled it correctly. The particle oscillates, you like that one? Means to go backwards and forward, backwards. Between x equals 2 and x equals 4, with a period of pi seconds. There we go. 3b.